Okay. Okay, so this is from practice problem number 8. So it says like, how many critical points could your composition function have given these two conditions? Like the gradient of f can't be 0, and then the determinant also can't be 0 for g. And so the idea here is that, like, let's try to assume that maybe we can be positive and say that, let's assume that f of g has a critical point or has critical points. If we assume that f of g has critical points, that means that what do you do to solve for a critical point? You always find the determinant and you set it equal to 0, right? Always. That's the first step for if you're finding critical points. So if this composition has a critical point, that means that this derivative set equal to 0 gives you something. But sorry, determinant. Oh wait, no, derivative. Sorry, yeah, this is the derivative matrix. Okay. Then by the chain rule, this is df dg equals 0. Then the second condition here says that the determinant of this derivative matrix is never 0, which means that g has to be invertible, or in other words, your dg inverse must exist, right? So that means that if we multiply both sides by dg inverse, we get that df equals 0, because 0 times dg inverse is still 0. But then the first condition said that the gradient is never 0. If the gradient's never 0, how could your derivative be 0? So this is a contradiction. Thus, we know that our assumption is not true. So f of g has no critical points. Any questions on that? Okay. Would anyone like to go over 12, which is like kind of like last week's material, like percentages and stuff? Yes. Okay. So from last week's recitation notes, I have this like nice chart. And so we know that if you ever see percentages, anything with like d like variable over that variable, that's how you're going to represent percentages. If it just had like dx, then it would say like, oh, it only changes by 0.10 or something, 0.2 or something. So if it's a percent, you want something of this form. So right now we need, well, we're going to need to find dp, definitely, no matter what. So we need to find dp, and dp is going to be the partial of p with respect to L dl, plus the partial with respect to m dm, plus the partial with respect to r dr. And you can find each of those things. So the partial with respect to L is going to be 2/3, L to the negative 1/3, m 1/3, r 1/3, dl. Plus the partial with respect to m is going to be 1/3, m to the negative 2/3, and you keep the rest the same, dm. And then dr is the partial with respect to r is going to be -1/2 r to the -3/2, and L and m stay the same. But the question doesn't ask for just like how much does p vary by. It asks for how much does p, like the percentage of p changing. So that means that we need to find dp over p, not just dp. So we can take this whole thing and divide by what p actually is. So L 2/3, m 1/3, r -1/2. And you know that you did something right if you find that things cancel out nicely. So like the first green term, you find that you end up with 2/3 dl over L. That means you've done something right because you have a dl over L. That's what we wanted. For the orange, you get a 1/3 dm over m. For the purple, you get half dr/r. This is what you want to see because you have a dl/l, dm/m, dr/r. And we're given that each of L, M, and R decrease by 10%. So this tells us that we're given that dl/l equals -10, dm/m equals -10, dr/r also equals -10. When you plug those into our expression, you get 2/3 times -10 plus 1/3 times -10 minus half times -10, and you get -5. Yes.
Why wouldn't it be like minus 0.1 or like yeah?
Wait. Oh, because percentages I said are always represented like this.
Oh.
So it can just be 10. Yep. And so this tells you that P decreases by 5%. So you just take the number percent. Any questions on that? Okay, so let's do some new material. Okay, slight review from single variable calculus. So in single variable calculus, there was a definition of a critical point. And we knew that a critical point could be where your derivative equals 0 or your derivative might not exist. So similarly, now in multi-calc, we have points where your partials may be 0 or your partials may not exist. And so a critical point, the first derivative test, is basically saying that a critical point is where both your partials are 0. So meaning that where your derivative equals 0, or where just one of your partials does not exist. Then those are your critical points. So the first derivative test just tells you how do you find these critical points. You set your derivative equal to 0 and solve. Then the second, so let me introduce the Hessian in order to introduce the second derivative test. So the Hessian is where if you assume that your first partials and second partial derivatives are continuous, you'll notice that your Hessian matrix is symmetric. And so this means, oh, I forgot to say that in order to like ease notation, this f sub x represents the partial of f with respect to x. So that's just so that we're not like writing partial f, partial x every single time. So like f of x, y is partial of partial x, partial y, like that, just for notation. So the Hessian is going to be in the top left corner. You have the partial with respect to x, ln x. Here is going to be x, y. Here's going to be y ln x. And here's going to be y, y. And as long as your derivatives are all continuous, this will be symmetric. So you only technically usually need to compute like half the number of terms. Okay, and the determinant is you take it normally, determinant of a 2 by 2 matrix. The trace is you just add the diagonals. Okay, so this brings us to our second derivative test, which tells us that if your determinant is greater than 0, it's going to be a local extremum. From there, you now have to look at the trace. If the trace is less than 0, you have a local max. If the trace is greater than 0, you have a local min. Now, if your determinant is less than 0, that's what's called a saddle point. So saddle point is kind of like in one direction, you find a minimum, but going in the other direction, you find a maximum. So it's kind of like you have two like things. That's what's called a saddle point. And if the determinant is 0, your test is inconclusive, and that point is degenerate. Okay. Any questions on the definitions before I do an example?
Yeah.
Yeah.
Like in the Hessian, how would you do like how would you do the diagonal? Like how would you do like the bottom left?
Bottom left. So if you had wait, I think okay, we're gonna do an example. I'll show you what it looks like in the bottom left. Okay, so I'm gonna keep this here, but I have a question, which is problem number 7. So it says that you have a function f of xy equals x squared. Let me just put it on the board for now. X squared y minus 3xy plus x squared x plus 1. And it says there are 2 critical points of this function, and find where they're located and like saddle points, max, mins, etc. So back to our definitions. So how do we find the critical points? The first step is that we want to find the derivative matrix. So the derivative is going to be, we need the partial with respect to x and the partial with respect to y. So partial with respect to x gives us 2xy minus 3y plus 2x minus 1. Wait. Minus 3. Partial with respect to y gives us x squared minus 3x. And then you want to set each of these things equal to 0. So what does this side give you? If you kind of manipulate it a bit. So let's get 2xy plus 2x over here. Minus 3y minus 3 equals 0. We see that this part has the 2 x's in common. So this gives 2xy plus 1 minus 3y plus 1. Now you have both y plus 1. So you can just write it as 2x minus 3y plus 1 equals 0. And so you get x equals 3 halves and negative 1. For over here, you get x minus 3 equals 0. X equals 0, 3. Yes. Sorry. Yeah. Y equals negative 1. And from here, for the x equals 0 term, if you plug it into this expression, because we want an x and a y, we want an x and a y so that both of these expressions are 0. So, so we need to find the y so that plugging x equal to 0 here will give us 0. So if you plug in x equals 0, you're left with negative 3y minus 3 equals 0 or y equals 1. So x equals 0 gives you y equals negative 1. X equals 3 gives you y equals to negative 1 again. So right now we have 3 critical points potentially, but this problem, right now we have 1 critical point, 2, 3 critical points. But you notice something weird, because if you try to plug in this point, 3 halves negative 1 to here, to this expression, what do you end up getting? You get 3 halves squared minus 3 halves, which is 9 fourths minus 9 halves. This is not 0. So it turns out that this point is not a critical point, because a critical point means that your derivative should be 0 no matter what. But this doesn't give you 0 in the derivative. Okay, so right now we only have 2 critical points we want to work with. And now we can classify them. So how do we classify them? Wait, why is it? Okay. So now we need to find the second derivative. So the second derivative, or the Hessian matrix. So the Hessian is going to be this with respect to x, like the partial with respect to x again. So that gives you 2y plus 2. This term, remember, this is partial with respect to y, partial with respect to x. So we see that we do the partial with respect to x first, that's this thing, and take the partial with respect to y. That gives you 2x minus 3. Remember this term up here? Was you do the partial with respect to y, then x. So you can take this. This is the partial with respect to y. Now take it with respect to x. You get 2x minus 3. So it's the same number. So they're symmetric. And then for the partial with respect to y twice, there's no y's here. So 0. And now you have 2 critical points. So you can plug in your 2 critical points. So d squared f at your first one is 0, negative 1. This gives you 0, negative 3, negative 3, 0. This determinant is less than 0. Determinant less than 0 means it's a saddle point. D squared of our second critical point, 3, negative 1. That gives us 0, 3, 3, 0. This determinant is also less than 0. So we just found that we have 2 saddle points. Okay. Any questions on that example?
What does a saddle mean? Like, I know that it's on the determinant is left, but like,
Mm-hmm. So
does
this.
it mean like graphically or like,
So the saddle point, I think it would. So okay. So let's go to like, you can visualize it. So we have x squared y minus 3xy plus x squared minus 3x plus 1. And we're looking at the point, let's look at 0, negative 1. So 0, negative 1 you see is kind of like, it's like this point right here. So you see it's kind of like in one direction you have like a max if you look at this part, but if you look at the upper part, you kind of have like a mean.
okay.
Yeah, so that is what's called a saddle. Like you see how it's kind of like swooping, like swooping in kind of.
Yeah.
Yes. Mm-hmm. Any other questions on this example? Okay, let's go into absolute extrema then. So, okay. Okay, so for absolute extrema, so when it asks you to find, so now we're gonna go into like parameterizing and the Lagrange stuff. So in general, when it asks you to find an absolute extrema, there's 3 steps. First step is you list all the interior points where f may have an extrema. So that's just using the first derivative to find all your critical points, step 1. Step 2, if they give you a boundary, you need to find any boundary critical points that might be possible. Now, if n equals 1, meaning that you just have a single variable calculus equations, like f of x equals x squared plus 2x plus 3 or something, then that's just like from math 104, where if you're finding the absolute extrema of this highlighted thing, you find the derivative, set it equal to 0, and they always gave you like endpoints, like on 0, 2, and you tested those endpoints. Now in multi-calc, we're dealing with where we have n greater than or equal to 2, meaning that we have more inputs. So if we have more inputs, we need other techniques. One technique is you parameterize the boundary, or the second one is you do the Lagrange multipliers. And in the third step, you want to evaluate f at all the points you found. So you will get like f of this point equals 2, f of whatever point equals 10. Whichever one is the largest number, that's your absolute max. whichever one is your smallest number, that's your absolute min. Okay, any questions on the overview first?
What does Lagrange multiplier?
We'll do, so Lagrange multiplier is just like the method of doing gradient f equals lambda gradient g. Yes. Yes, so for n equals 1, we're not focusing on n equals 1 because that's like a math 104 thing. So n equals 1 here, you see how f I define like as x1 dot 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 xn. So if n just equals 1, that means you just have f of 1 input. And so that's like a normal equation we know how to do. But now we're dealing with like say n equals 2. So then you have like an xy, where you have like xy plus 2x, whatever. That's what the equations we're dealing with now. Yep. Okay, so let's do an example. So here's example 1. So we're trying to find the absolute extrema of this function over a triangular region bounded by these 3 lines. Okay, so I'll give you a minute to read the question and think about it while I erase the ball. Okay, oh, before we get into that example first, I should have explained what we're doing first. So the first method we're going to do is parameterization. So the intuition behind this is that we have a function with 2 variables right now, but we're not familiar with how to take like how to do things with 2 variables. We like things in 1 variable, so that's easier. The idea is that we're trying to parameterize whatever boundary we're given so that, and let's call it like x of t, y of t, so that our actual function will just be an equation in terms of 1 variable. And we know how to solve like equations with 1 variable because that's like math 104 stuff. So that's our idea. So let me do the example. So first step is that we want to find interior points, right? Okay. And how do we find the interior points? We take the derivative and set, or the gradient and set it equal to 0. Gradient or derivative. So we have the gradient with respect to x. Well, that gives us 2 minus 2x. Gradient with respect to y gives us 4 minus 2y. And we want to set that equal to 0, 0.
It's the gradient of the
Either is fine. For derivative, you just set it just be horizontal. Okay, so from the first line, you get 2 minus 2x equals 0, or x equals 1. Second line, you get 4 minus 2y equals 0, or 4 equals 2y, so y equals 2. So our first critical point right now is 1, 2. Second step, we need to find the boundary points. So let's call it like 2a. Let's first know what this thing is. Right now, they're telling us that the region is this triangle. So y equals 0, that's this line, y equals 0 line. X equals 0, that's this line. And then the 9 minus x is this line. And so we have a y-intercept of 9, x-intercept of 9. So first part, let's parameterize the y equals 0 line first. So I'm going to take, we have our line, y equals 0. We need to parameterize it. So what is the domain of our line right now? The domain is x goes from 0 to 9. Because right now, y just has to be 0, but x can be anything as long as it's from 0 to 9. So for the parameterization, we're going to choose x can be anything. It could be any t from 0 to 9. Y is always 0. It says it's always 0 no matter what. And so putting this together in one single equation, so we want to evaluate x with parameterization. So in our function here, we have 2 plus x is now t. So 2t plus 4, y is now 0. So 0. Minus x is now t, and y is 0. So our new equation is negative t squared plus 2t plus 2. And now it's an equation in terms of one variable, which we know how to do things to. Okay, and so now we can just take the first derivative to find the critical points. First derivative is 2t plus 2. Set that equal to 0. We get t equals 1. Okay, so in total, from this, like taking the derivative, finding the critical point, we found t equals 1. And let's also consider like the corner points, our domain. So let's consider t equals 0 and 9.
Wait, where did your t squared go? Where did your t squared go?
I took the derivative.
Oh.
So negative 2t plus 2. Yes.
When you're doing t equals 0 and 9, are you kind of just thinking about it as t is x, or are you actually looking at it as t is something?
T as x.
So
So x can be 0, x can be 9, but our parameterization calls it t, so t is 0, t is 9.
oh yeah, but if this was a different question where t and x weren't equal, we'd be looking at x's and right?
So
Like for example, if x was 2t, would you still be looking at t is 1 and t is 9, or would you be looking at whatever it solves to with x being 0 and x being 9?
whatever it solves to being x equals 0, x equals 9. Yes. Okay. So that's like using the parameterization of the line y equals 0. Okay. Let me continue the rest of the lines on my iPad. So we did the y equals 0 line. That's this orange line. We also have to parameterize each of the other lines. So if you take the green x equals 0 line, parameterizing that, well, x is 0, y can be anything from 0 to 9. And so you do the same thing. You find a single equation with one variable, take the derivative, set it equal to 0, you get t equals 2. And then we also consider the domain. Then for the y equals 9 minus x line, now we can call x like t. If we call x as t, then y will be 9 minus t. And we do the same process again. Put it all in one equation, take derivative, set it equal to 0, we get t equals 4. So now in total, we have, remember our critical point from the interior. We have these 3 from the boundary. We have 3 from this boundary, 3 from this boundary. So in total, I listed all of our points here. Also, don't forget, we need to test the corner points as well. So like the corner point, this one, and this one. And so we have all these points. We evaluate them at our original f, which is that like 2 plus 2x plus 4y thing. And we find the greatest value, which is 7. So there's an absolute max of 7 at 0.12 and absolute min of -61 at this point. Yes.
There is a number confusing why you will yield the critical points of like 1, 0 from the y equals 0. And the concept part.
So it's kind of like, so this first part, the critical point for just the interior, that's like finding like some critical point in the interior. But then we also have to consider the boundaries. So like parameterizing the y equals 0 line and finding that critical point, that's like saying, oh, this point is also could be a critical point. Or like this line here, maybe like this point will also be a critical point. So it's kind of like if you have in single variable calculus, if we had from -1 to 1 of x squared, and then you find like, so f of x equals x squared, we find the derivative, which is 2x, that it equals to 0, and get x equals 0 as a critical point. But if we wanted to find the absolute extremum on -1, 1, then what would we do? We plug in -1, we plug in our critical point, and then we plug in 1. See what they give us. This is 1, 0, 1. So then here it turns out that the absolute max wasn't in the interior, it was on a boundary point. So that's the same idea now, just we're in higher dimensions.
You go up to like when you parameterize x, you can do.
The green. Any other questions on this problem? Oh, yes.
So like one of the critical points is that they were repeated. So like you don't have to write them down.
Yes, so for this method where I like parameterize each part, oh sorry, are you okay? Then I had all these points and they're repeated. The only reason they're repeated is because for each parameterization, we looked at like the domains too. So that's why they're repeated. In my notes, I have like a method 2 where they end up not being repeated. So like you just don't consider the domain, but you don't want to forget to make sure you consider the critical points. Like that's the main thing. So if they're repeated, that's fine because you don't have to keep calculating that value. Yes?
You get 0 and 9.
Yes, 0 and 9 is from the domain. Yes. Oh. So I just like try to make sure I'm checking everything. Like if I was just looking at this one specifically, it's kind of like I'm finding the point, the critical point in the interior, and also considering the endpoints. So it's like making problem. Yes, I'll do the second example. I have a disk. Wait, is she asking?
With the finding the like boundaries and like the 0 and 9 and whatnot, would it have been okay if you just noted that each of those corner points that all that and you go to each
Yeah, like you don't need this. Yeah.
Okay.
Oh, sorry, you were.
Yeah, like I get how you find all the different t's for like the y.
Uh-huh.
The y equals 0, x equals 0, and 9 minus x.
Uh-huh.
But like, how then did you get like f equals 1, 0, f equals 0, 0, f equals 1?
Oh, I plugged it into the original f. So like, for example, 1, 0 point, our function at the very beginning, very beginning was this function.
Oh, okay. You plug them into that.
Yep. So you plug it into the very original function. Yeah. 9 minus x.
Find the slope, get a point, make an equation, plug that equation into stop there, get x. You know what I mean?
Yeah, I see what let me
Or how did you,
x.
is there easier way or
I think even if you do your way, like find the equation of that line, the equation of this line is y equals 9 minus x itself. So like the actual line is y equals 9 minus x. Oh, I guess if you're thinking of that way, then like if you're thinking of x equals x, then yeah, then this itself is its parameterization.
Yeah, and then
Yes. Yep. So I just called it t so that you can recognize like, oh, we're parameterizing this as our new variable. Okay. So let's do the second example then. Okay, find the absolute max and min values of this function on the unit disk. So I won't do this whole thing out, but I'll show you how to parameterize it. So first step, we find the interior critical points, that's fine. Boundary points, if we wanted to parameterize our equation. So we have x squared plus y squared equals, is less than or equal to 1. Okay, let me just do it here. So we need some sort of x of t and some sort of y of t, so that plugging them in satisfies this x squared plus y squared equals 1. And so does anyone know any like identities, maybe trig identities? Yeah, so we're gonna do polar parameterization here. So like if we chose x of t equals cosine of t, y of t equals sine of t, notice that if we plug it in here, we get cosine squared plus sine squared, which is 1. So the parameterization we're wanting to use is going to be x of t is cosine, y of t is sine. Once we have our parameterization, we follow the same steps again. So our parameterization, cosine and sine, plug them into our original function, that's this step. And so now we have an equation with just one variable t. You take the derivative, set it equal to 0, get your critical point. That makes sense? Yes.
So for clarification, we usually find set the parameter with the boundary equation and then plug it into the.
Yes. Because right now in like one boundary equation, we have 2 variables, but we want one variable. So we plug those in for original function. So, but I have a question. If the question said find the absolute max and mins on the unit disk, like, and it said the disk was, let's see. If it said the disk was this, like ellipse or whatever, what should I use for x and y? Yes. Yep. Because we want something so that when we plug it in, this equation is held true. When you plug this in here, you would get 9 cosine squared over 9. The 9's cancel out. And then plus sine squared, which is 1. Yes.
I only asked this on a practice problem. How would you parameterize it if it was equal to 25 and forget the 9 and the over 9?
Okay. So 5.
Yeah.
Anyone have idea? Yes.
5 sine.
Yes. X equals 5 cosine and y equals 5 sine. Because you get 25 cosine squared t plus 25 sine squared t equals 25. Yeah, 1. You could also think of it as like if you didn't know, divide everything by 25, and then we get the same column as what I just said before. So it's just like the 9. Yes.
I have a question. When you write on the unit disk and then you use the curly brackets, you're saying like how do you read that notation?
Oh, it's like all points x, y such that this equation is held. So like all points on this circle, basically. Yep. Okay. Let's do a Lagrange multiplier. Lagrange multiplier. Okay, wait. Let me mention one thing. I think is on the prep quiz. Oh wait, did Rimmer explain like question 8 to you guys? Okay, that's fine then. Okay, or let me just summarize. So the idea is that like f of x is like xy, and then you want to find the like level sets. What do you do to find the level sets? You set your equation equal to c. But we don't know what x, y equals c looks like, so let's solve for y. So all the level sets look like c over x. And so for any c over x, here in the black lines, I made those my level sets. And then your constraint they told you is ax plus by equals c. Like I also don't know what that looks like, so let's solve for y. It's going to be negative a over b x plus c over b, something like that. And so it's a line that has a negative slope. So it looks like this. And if you imagine walking on this line constraint, you see that first. So following like, so you see that first you touch this level set. So you touch the y equals 0.02x level set here. Then you keep walking along the constraint and you get to this level set. You get to the y equals 0.05x level set. And then you keep walking along the constraint, you get back to this 0.02 level set. So you went from a lower level set to a higher level set to a lower level set. So this is a max. Okay, any questions on that? Okay, so let's do Lagrange. Where did I color this? Oh, note that if it says a circle, that means it's just like the outline of it. A disk is always filled in. Okay, Lagrange multiplier. So the typical question is always going to ask like, find the extrema of a function subject to some constraint. And so the idea is that we're going to do, first step is write this equation. Second step is always the last step, is that we evaluate f at all the points we find. So let's do this first. Let me do this. Let's do this one. So it says find the absolute extrema of f over R, where f is this function and your region is this. So your region now is a disk again. Okay, first step, you find your interior critical points, which always means that you find the gradient, set it equal to 0. So we found the gradient and we got that a critical point is 1, 0. Then step 2, we look at our constraint. So our constraint right now is this region. I want to set it equal to 0, so I subtract 4 on both sides. So our constraint g is going to be x squared plus y squared minus 4. Then in this equation, so we have gradient f equals lambda gradient g. Gradient of f is 2x minus 2, then for y, gradient of g is 2x, 2y. So now we have 3 equations in total. So you want to take the equations you get from this gradient thing. So we have the first row, which is equation A. The second row is equation B. And then your third equation is always that constraint. So we have 3 equations right now. From this first, I guess I started at the second equation, B. So I have 4y equals lambda 2y. I want to have lambda by itself. So I divide both sides by 2y. So I have lambda equals 4y over 2y, which is 2. But note that I divided by 2y. When I divide by 2y, well, what if y ended up being 0? Then we'd have something like dividing by 0, which is an error, right? So we need to test, is y equals 0 possible? Well, if y equals 0, what happens to our constraint? if y equals 0, we plug it into our constraint, we get that x squared equals plus minus 2. There's no contradiction there. So it turns out that we have 2 extra points coming out of this that we need to check for, which is 2, 0 and negative 2, 0. Then from equation A, so the first equation, we do the same thing. Or, oh, actually I plugged in lambda. So you could either like solve for lambda, set them equal to each other, or solve for one lambda, then plug it into the second equation. So here I plug in the green lambda into our first equation to get x equals negative 1. Now I have x equals negative 1. So let's plug that into our constraint. So if I plug it into our constraint and solve for y, I get y is plus minus 3, square root of 3. And so from this, we have 2 critical points, negative 1 square root 3 and negative 1 negative square root 3. So in total, now we take all those points that we had. So we had the negative 1 square root 3, negative 1 square, negative square root 3, and then the 2, 0, negative 2, 0. And remember from our like interior point also, we plug those into the very original f, see what outputs we get. And we see that the greatest value is 9. So we have an absolute max of 9 at those 2 points, an absolute min of negative 1 at 1, 0. Yes.
So if we have like an interior saddle or whatever, how would we like when we're plugging everything back into the app to decide what is what? How would that factor into our analysis?
Interior saddle.
Like from the to the 0 to the back to the 0.
So in this question, I haven't seen one where you have an interior saddle yet, so I don't think,
Isn't the only way to get a saddle?
yes, possibly. But
Or, like, we didn't really check it, but we didn't look and stuff. Like, it could like give us a lowest point, I guess, when you're doing the last part, like when you just did the analysis, but
mhm.
we don't check really, I guess, with the action. So do you just assume it's an absolute?
Well, if it ended up giving you a saddle, then this wouldn't like be the lowest number possible.
Okay.
So it will either be like the largest number is max, lowest number is min. Okay. Any questions on that? Yes. From the caution, like the caution check to see if y could be 0 or not.
Oh, okay.
Yeah.
And then
Okay, let's do that example. So here I have this example. So it says find the points x, y, z on the hyperbolic cylinder, so some cylinder, that are closest to the origin. So there's an example in the practice problem that's similar to this, where you're trying to find like the points on some line closest to the origin. It's the same idea. So this, okay, let me give us like 30 seconds to read it. Okay, so we're trying to minimize the distance because we're trying to find some random point that is closest to the origin. So if you have some point on this cylinder, like x, y, z, and you want to find the closest x, y, z that is closest to the origin, 0, 0, 0, then how do you find the distance? The distance is the normal distance formula, which is square root x squared, because you have x minus 0 squared, plus y minus 0 squared, plus z minus 0 squared. So this is your distance formula. But we don't want to like take the derivative of this and find critical points because there's square root, makes things weird. So it turns out that if we just take like the what's under the radical and optimize that, it'll give us the same answer. Or like it's the same as optimizing the square root of that. So we take f of x as this equation, and our constraint is that our point has to be on this hyperbolic cylinder. Like it has to be, we can't just take any x, y, z. It has to be on this cylinder. So our constraint is that equation. Our point has to be on that equation. So step one, there's no interior because it just says it's a hyperbolic cylinder. So it's like the outline of our shape, where there's no like inside. Whereas when we had like x squared plus y squared less than or equal to 4, that's a disk, because that's saying that you have the x squared plus y squared equals 4 part, and you also have the interior, because less than or equal to. So then you do Lagrange. So we have the gradient of f equals lambda gradient of g. We get 3 equations from this, plus our constraints, so total 4 equations. From the first equation, we have 2x equals lambda 2x. When we divide both sides by 2x, we get lambda equals 1. But because we divided by x, let's check if x can be 0. Question mark. Well, if x equals 0, say we plug it back into our first equation, we get 2, 0 equals lambda 0. We get 0 equals 0. That's fine. But you always want to plug it back into the constraint to see if you get a contradiction. So back to our constraint here, x squared minus z squared minus 1. If we plug in x equals 0, we get negative z squared minus 1. But z squared itself, z squared is always positive. Like any number squared is positive. So negative of it will always be negative. And then you have a negative number minus a negative number. How can you get 0 if you have a negative minus negative? This can't happen. So it's a contradiction. So we don't need to worry about any points coming from that. Then you keep doing the same thing with the rest of the equations. So second equation, you get y equals 0. Third equation, you get z equals 0. Plug it back into the constraint to get x equals plus minus 1. And so you have 3 critical points, 0, 0, and with x is 1 and x is negative 1. The last step is you always plug these 2 points back into your original function. And remember, our original function was this distance one. And turns out that you get 1 for both. So you have an absolute min of 1 at both of these points. They're both closest to the origin, and they're on your hyperbolic cylinder. Yes. Lambda is from the orange lambda. Because that gives you 2z equals negative 2z, and a positive number cannot equal a negative number, so it only happens if z equals 0. Because if you test like if z equals 1, you get 2 equals negative 2. That can't happen. If you test z equals negative 1, you get negative 2 equals 2. That can't happen. So in order for this to hold, you need z equals 0.
For lambda using z and apply that state, apply the same thing to
Like starting with the purple. Oh wait, you mean like lambda equals negative z? Lambda equals negative 1. Okay. Lambda equals negative 1. Then, so if you did that, that means that you'd be starting with this purple and you get lambda equals negative 1, and you have the green, and then you would do the orange next. So like if we hadn't done this step yet, then you would do the orange next, which gives 2x equals lambda 2x, and lambda equals negative 1. So you get the same conclusion that x is 0. Oh wait. That gives a different So that gives x equals 0. But that just kind of like switches the points around. So you probably get like 0, 0, 1 or 0, 1, 0, and the distance will still be 1. Yeah. Okay, wait. If you solve that, so you get then get this. Then you plug it in, so you get b squared minus 1 equals 0. B equals plus minus 1. So instead you get 0.001 0, 0, negative 1. So then I guess these 2 points would also be closest to the origin. And on your hyperbolic, wait, is it still on the hyperbolic 0? Yes, it's still, wait, 1. Yes. Yes, but I think we were trying to do like if none of this had happened and we started with the purple and then like did the other a different order to see if it would work. But actually this might not work because if you're saying that 0.001 is closest, plugging this into our hyperbolic cylinder, you see that you'd get 0 minus 1 minus 1 equals 0, but that's not true. So it's not actually an answer. Yeah. So stick with the way I started it.
We always do the first one first. And just
Yeah, just like work down usually. Yeah.
Like you chose not to use the square root x squared
Uh-huh.
y squared plus.
Yes.
So like can you always like just take the inside outside function and then substitute that mode to that?
You should only do that for distance. That's where it shows up. Yeah. Yes.
Why can't x be 0 but then c can't? They're like the same.
V equals 0.
It's not because in the original function, if you plug in 0 for x, you can still solve for plus or minus.
Okay. Yeah. Okay. We went over time, so recitation is over. Let me stop the recording.